Geometric properties of conics. First one has to do with the chord of contact. So if the chord of contact comes from a point on the directrix, so that external point is on the directrix, then the chord of contact will turn out to be a focal chord. So it'll pass through the focus. So I'm going to do it for the ellipse. You notice I haven't specified a conic here. It's true for all conics. But let's have a look at the ellipse. Okay. So if it lies on the directrix, my external point then, instead of calling it x0, y0, I'll give it the x value of the directrix, a over e. Chord of contact will now have the equation. Well, we know the chord of contact, remember, it'll mimic the equation of the ellipse. So normally it would go x0 x over a squared plus y0 y over b squared. But instead of x0, we've got a over e. So we come x over ae plus y0 on b squared is equal to 1. So that's the equation of the chord of contact. Well, we want to prove this is a focal chord. So if I substitute the focus into the left-hand side, hopefully it'll turn out to be 1. And sure enough, we get AE on AE, which is 1, plus 0. So yes, it does go through the focus. So focus does lie on our chord of contact. All right. Now this one, well, we'll draw a diagram in a sec so you can see exactly what it means, because sometimes it's hard to get your head around it. That part of the tangent between the point of contact and the directrix subtends a right angle at the corresponding focus. All right, let's draw the picture. Again, I'll do it for the ellipse. All right. That part of the tangent between the point of contact, which is P, and the directrix, so T, subtend. Remember, subtend means 2 points joining up to a third point. It will subtend an angle. So we're joining up to the focus at this time because it says subtends at the focus. So basically, we want to show angle PST is 90 degrees. We want to prove that that's a right angle. All right, well, we know the equation of a tangent. I've got it in its parametric form. So x cos theta on A plus y sin theta on B is equal to 1. So I can find the coordinates of t. We know the x value is going to be A on E. So if I substitute that in, we'll be able to find the y value. And a little bit of rearranging to do that, but I come up with this expression, B outside of E minus cos theta over E sin theta as the y value. So there's the wonderful coordinates of t. And the coordinates of the focus, of course, is AE naught. So I've got the coordinates for each. We want to show that it subtends a right angle. So I could do it by saying, oh, well, let's find out what slope PS times slope ST equals. Hopefully, it'll be -1. Okay, slope PS, B sin theta minus 0 over A cos theta minus AE. That tidies up to be B sin theta on A cos theta minus E. And slope TS. A little bit more work to do here to tidy this one up. Fractions on fractions, yuck. But if I multiply top and bottom by E sin theta, that would get rid of it, wouldn't it? Oh, I've just inverted and multiplied. Fair enough. So I've inverted and multiplied, but turning the bottom one into a complete fraction. E will cancel and so on. But not all. E, A, 1 minus E squared, actually that's very similar to something we've seen. A, 1 minus E squared. What is that very close to? Anyone recognise it? So what would we like that to be? I mean, it's not what... Yeah, if it was A squared, then A squared, 1 minus E squared, we could just substitute B squared into that. But that's all right. I could multiply top and bottom by A and make that A squared if I need to. So there we go. That's what I've done. For some reason, I put it over A. Why did I do that? Why didn't I just put A on the top of the fraction? Just to make it look more complicated. Okay, so there it is now on the top. But what I've also done is I've said a squared 1 minus e squared is b squared, so I've cancelled the b squared with the b. So, all right, so ps times ts. Looking back at that, actually, I probably should have made a note there that b squared is equal to a squared 1 minus e squared, because it's not immediately obvious why that just disappeared. So if I'm doing a solution, it could look like I'm fudging it. So I probably should have explained that I've used b squared is equal to a squared 1 minus e squared there. All right, so now I'll multiply the two slopes together, and you see it comes out quite nicely. The b's and the b's and the sine theta and the sine theta, a with a, and the cos theta minus e cancels with the e minus cos theta, leaving me with minus 1. So yes, indeed, PST turns out to be a right angle. Reflection property. Now this is the fun one. Did I show you that elliptical pool table last year?
Oh, yeah, you did.
Remember that?
Yeah.
So this is basically the reflection property of the ellipse. The tangent to an ellipse at a point P is equally inclined to the focal chords through P. So again, let's draw a diagram so we can see what it's talking about. There's our ellipse, tangent through the ellipse. Oh, we'll put in the foci. Voila. So what we're basically saying is the angle of incidence is equal to the angle of reflection. If you do remember that video from last year, remember the pool table they made where the hole was at one focus and they put a dot at the other focus, and then that way they could always theoretically get it in the hole. Of course, in the real world, there are other things to take into account, friction and how hard they hit it and things like that. But if they hit it with the right force, it always went into the hole. Now I've joined up also S to T and S dash to T so I can make use of what we just proved, because we know that angle PST and angle PS dash T dash will be 90 degrees, because that's what we just proved. That part of the tangent from the point of contact to the directrix subtends a right angle. So that means those two triangles are in fact right angle triangles, and that may well be useful in this proof. So we're going to prove angle SPT is equal to S dash PT dash, and just like when we did it with the parabola, remember that's not actually the angle of incidence and the angle of reflection, but if I can prove they're equal, then the angle of incidence and the angle of reflection must be equal. The angle of incidence and reflection is to the normal, not to the tangent, apparently. So science teachers tell me. I'll take their word on that one. But as I say, if we can prove these angles, then it's very easy to say, well, 90 minus, 90 minus. Okay, going to construct a third parallel line, which goes through P. Oh, in fact, it's a fourth parallel line if you think about it, because I've got the y-axis as well. Right. I've then drawn a horizontal line in through P going to the two directrices. Now I know that PT over PT dash will equal PN over PN dash. That's just ratio over the intercepts of the parallel lines. Remember, it doesn't matter where you put the transversal, you'll always cut it in the same ratio. So ratio of intercepts. But if I rearrange that, I get PT over PN is equal to PT dash over PN dash. Okay. But of course, I also know that eccentricity times Pn is equal to Ps, definition of the conic. Right? Distance to the focus is equal to eccentricity times distance to the directrix. And similarly with the other focus and directrix, the S dash and the N dash. So I can sub that in. Well, both are over E, so I can get rid of that. And I now have this ratio. PT over PS is equal to PT dash over PS dash. And now I can look at those triangles because they are sides in those triangles, which we now know also from the last theorem to be right angle triangles. Right? So we proved that those angles were 90 degrees. Right? That was our property we just did. So PT over PS is in fact the secant ratio of SPT, and PT dash over PS dash is the secant ratio of S dash PT T dash. Remember, secant reciprocal of cosine, which means it's hypotenuse over adjacent. Well, we know they have to be acute angles because we're talking about inside a right angle triangle. So therefore those angles must be the same. It's not like one could be obtuse and one could be acute. They both have to be acute angles. And if their ratios are the same, they've got to be the same angle. So angle SPT must equal angle S dash P T dash. Ah, yes, this is quite nice, this proof. This next one, PS plus PS dash is always equal to 2A. Now, I could go and use the distance formula. XY, we got S would be AE naught and S dash. But it is always easier to find the length of a horizontal or a vertical line than it is to find an angled line. So if P to S would be the same as eccentricity times P to M. And P to M is a horizontal line, and that's a lot easier to find the distance of because all I've got to do is subtract the X values, and then I know how long that line is. But I could do the same for P to S dash. It would be the same as P to M dash. And again, we're talking about a horizontal line. And in fact, I don't even need to work out P to M and P to M dash because if I add the two together, it's meant to be, use your imagination, it's meant to be one straight line there. I'm sure that's a straight line. From M to M dash, so it's just the distance between the two directrices. So we have E times 2A over E, which is 2A. So a lot quicker there to use the horizontal line. So it's a technique which is definitely used for this particular one, but you'll find that useful in other properties. If you have to find a focal length, sometimes it's easier to say, oh, hang on, that focal length will be the eccentricity times this horizontal length, and the horizontal is an easier one to find. Well, that brings us to this sort of question then. Back to complex numbers. The modulus of z plus 2 plus the modulus of z minus 2 is equal to 8. That's an ellipse. Reason. Let's go back to this. What is it saying? The distance from P to one point plus the distance from P to another point is equal to a constant value. And we end up with an ellipse. All right, let's have a look at our question. Whoop. Modulus of z plus 2 means distance from z to minus 2. Modulus of z minus 2 means distance from z to positive 2. So the distance from z to one point plus the distance from z to another point is equal to a constant amount. It's an ellipse. We just got to work out its equation. Okay. So I'm using the idea that the sum of the focal lengths, I'm saying these two moduli are the focal lengths of an ellipse. And I know the sum of them will be constant. Therefore, 2a is equal to 8. So I know a is 4. That's one part of my equation. I now need to work out b. But hang on, I know the focus is AE. But our two foci, if you like, are 2 and negative 2. So AE is 2, giving me the eccentricity as a half. That now allows me to find b, because b squared is equal to a squared 1 minus e squared. Subbing in, b squared is 12. I'm actually not going to worry about finding b, because of course the formula for an ellipse is on b squared, not on b. So I don't really need to know b. So there's my ellipse. X squared on 16, x squared on a squared, plus y squared on b squared is equal to 1. Right, we end up with a beautiful ellipse. All right, time to play. We have some Patels and some Cambridge.